So we will continue with the next example, and in this case we have exactly the same transimpedance amplifier, but this time we cannot use the DC feedback loop existing in the design because the BDS was very low. For instance, the required output voltage swing was much larger than the BDS that we got, that was around 400 or 370 millivolts. So if we need a different BDS, for instance, like 0.9 volts or 1 volt, then definitely that will not work. So in those cases, then we cannot reuse the negative feedback loop in the design, and we have to create a new one. Okay, so how do we do that? So what we do then, it is we have our transistor here, okay, for our signal path, and then for the first we need to break this feedback loop. Okay, we cannot have both competing. And then we create a new one, and how it works, the new one. Let's put the other components that we have. So we have the source here and here. So the new one will basically do like this. We need to extract the DC at the drain, and for that we can use a low pass filter. And we will need to put a very large resistor so that it doesn't load the output and reduce substantially the gain. And then we need to use a correction amplifier. And then in this correction amplifier we connect one of the input at a voltage reference, and this is the voltage that we want here at the drain. And then we feedback this voltage to the gate, and naturally it has to be high impedance at the output so that it doesn't change the dynamics of this amplifier. So the voltage is coming with a high impedance, and then here I have to be careful. It is with the signs, because this is a negative feedback loop. So let's do this exercise here. Let's check if I have plus minus here, and then this signal at the output is a plus. It is going back on the feedback plus. The single stage transistor connected as a common source will invert this signal at the output. So the transimpedance is an inverting amplifier. It will put minus. The filter will not change the sign, so this is still minus. So we have negative feedback, minus coming to plus. Okay, so that is the correct connection. So the small signal of the amplifier, so we can see it here. We have a single stage. Okay, we don't need to implement a complicated amplifier here. There is no very strict requirement for the voltage at the drain. So if it is close to our target, let's say for instance if it is 0.9 volts, it really doesn't matter. It is a few millivolts up or down, so the loop gain of this amplifier does not have to be very large. So typically the implementation of this amplifier is just a single stage with not so much gain, because now we are worried it is the stability. So we are morely considering the noise and basically stability. Single differential pair here. So as our correction amplifier, the filter it is here, low pass filter here. And then we tested if this is minus at the drain, it will be plus. We follow, this is plus, it is converting into minus here, and then the filter doesn't change, it is minus. So, and this is the plus terminal of the amplifier, so it is correct. It's a negative feedback system. It's a negative feedback system, and then we have to do exactly the same things that we did before. We have to check the loop gain. We have to check the position of the poles and check that the system is stable. So everything that we did for the signal path here, we also have to do for the DC feedback loop. So the advantage here is that we are normally just concentrated on making sure that the DC is set to the right voltage, so it is only low frequencies that are relevant for us. So we have less concerns of stability problems at very high frequencies, because we just cut the gain at high frequencies, and for that we have this low pass filter. So we're going to check the small signal here, or small signal model here is here, and I just prepare the test for closed loop gain and loop gain simulation. So we just run this test here very quickly. And then we first check the position of the poles to make sure that for the closed loop gain. In the closed loop gain, we have that the total gain, and then I am measuring the gain from this voltage source to this node that I call the BB-CMFB here. So the total gain from my reference voltage to the input of the other side, I expect it to be 1. Okay, it has to come the same voltage at the output. So and the total gain, it is 1. It is 1, and it has a bandwidth of around 1 megahertz. So it is settling quite quickly. I check the position of the poles, and actually I can drop the zeros also in the same plot, because very likely some of these ones are going to fall exactly over the zeros are going to fall over the poles, and then well, we have it here as the following. We have a pole at almost 2 megahertz, and then these two poles that are located roughly in border positions. So the system, it is very stable as it is right now. If it were not stable, probably we will need to do some compensation using the techniques that we studied before, adding for instance a series resistance here to this capacitor, or reducing the gain, or we can try several things there. We check the loop gain here, and we have a simulation of the loop gain, again the position of the poles, and then we have the loop gain in dBs, and then the phase here. So this can also be done with the STB simulation in Cadence. We can do it very quickly here. We have gain and phase. Although we already checked that this is totally stable, we can double check if you want with the simulation of gain and phase, and then we see that at 0 dBs there is a 90 degrees phase shift. So this system, it is stable, pretty much stable. It's a single dominant pole. Okay, so this will basically make my correction amplifier. Now we need to go over all the steps again of biasing, but I'm not going to do that again. And here we can see the implementation of the biasing. So very quickly, we have the current mirror here and here that we have already discussed. So this is nothing new. The reference here, it is being mirrored here, so that has not changed. And now we have to implement the second amplifier, this correction amplifier for the DC feedback loop, and that amplifier is here. So what I did here is that I have basically a differential pair here, and instead of just having it with one terminal connected to ground, this one, I decided to use a current mirror load so that it improves the loop gain. So it will move a little bit the position of the poles, and change a little bit of the loop gain, but it works a little bit better. So I just added the current mirror load here, and this is basically the final circuit. So for the differential pair, I need a current source, as we were going to see very soon, and that is coming from another branch of the current mirror. So I have this one mirrored here. I could have probably also taken it from this reference, but I have to be very careful. I have to be very careful when I reuse one diode connected reference for several points in my sequence, because it can result on instability. So very often you will prefer to have separate branches for different current sources. Same thing, I am filtering the noise for this current source here, and yeah, this is basically the implementation of this DC feedback loop. You don't want that this amplifier consumes a lot of current, so you will want to have very little current flowing here. But that also comes as a price. If the current that it is biasing the correction amplifier, the DC feedback loop amplifier, is very small, we have an important detail to consider. If you notice here, these are basically the coupling capacitors here. The value of these capacitors becomes important. This will basically set the high pass filtering of the circuit. But this capacitor now, this capacitor is working as a current controlled voltage source. So the output current that comes from this correction amplifier will be charging this capacitor to the value that it is needed for VGS to match the 20 microamp current. And if the current here it is very small, so this is the maximum available current that will pass here. If the current is very small and the capacitor is very large, then it will take a lot of time for this capacitor to charge. So there is a trade-off there between the size of this capacitor and the speed in which this capacitor can be charged. So we cannot really make this current extremely small without considering the time that this capacitor will charge. So this is something. In this particular case, I put 50 picofarads, but I could have also changed the current to something larger, and then I could have larger capacitors also here. Let's take a look to simulation to see how the circuit behaves, and then we have our circuit implementation here. So we'll launch the ADL. And then I will be basically running this operating point in noise performance AC, pulse 0, and some transient. And then now I am a little bit concerned about the stability of the second loop. We have already studied the stability of the first loop of the amplifier. Now I will want to check the stability also. In addition to that one, I will want to check the stability of my DC DC feedback loop, and for that I will be analyzing the pulse zeros from the reference. Here I have a reference of 900 millivolts. How does the pulse look from this input voltage to the output here? Because that will tell me how the amplifier it is behaving. And another thing it is that I have added this pulse voltage here, so I want to test the transient response, if it has overshoot, if it oscillates. So I will be adding 100 millivolts pulse to the 900 millivolts DC that I have, and check how the loop behaves, how much overshoot we have in the out. Okay, so we'll be running the simulation. Okay, and then let's start with the bandwidth of the amplifier. Let's see what is the effect of having this DC feedback loop on. Put this in log, and then we see that we have this low pass filter, and it is a few kilohertz right now, and that is given by the size of these capacitors at the input. And then we have that the gain has dropped a little bit, and remember that now we have added this resistor here that it is loading the output. This resistor it is being shorted to ground by this capacitance, that it is 5 picos, so high frequencies this start to short this terminal of the resistor to ground, and then it start to load the output, and then so it will start affecting the total gain of the amplifier. So it drops a little bit, but it is a single stage. I shouldn't expect that it approaches the nuller, so it is expected that some degradation will happen there. It's not much. I think it is okay. Then let's go to the transient. So let's examine, before going to the transient, let's take a look to the DC operating point. So we go here, DC nodes voltages, DC operating points. So let's check if our amplifying device is 20 micro as I expected. The drain to source voltage, it is 900 millivolts, the one that I set with this voltage source here. I set 900, and then it is producing almost 900 at the other side. So my loop it is working. My loop it is doing what I expect. The current consumption of the correction amplifier, it is only 50 nanos. So in the worst case there will be only 50 nanos that charge these capacitors of 50 picos. So you can see that depending on the size of this capacitor and the available current here, the charging or discharging of this capacitor will be slow. So this is some consideration to take when deciding the value of the capacitors and the current. Okay, now let's take a look to the transient. So over these 900 millivolts, I sent the 100 millivolt step, and the step response we see it is totally stable. It is totally stable. So the compensation that I did is working very well. Now let's take a look to the poles and zeros, and yeah, for that what I'm going to do is I need to configure the pole zero simulation so that this is going to be my input. Voltage source will be the input, and then I will be analyzing here the output node. So I will be analyzing the poles and zeros of the transfer function from the input of the correction amplifier to the output, and see. And that configuration is here. So you can notice I changed the input source as a voltage, and before that it is this voltage source. And the results we can take a look here. We see that we see that the amplifier is stable, and there are some poles in butterworth positions here, and then all the poles are basically in stable positions, and that is basically confirming me that this transit simulation that I run has to be without overshoot and totally stable. Okay, so this is the total implementation of the transimpedance amplifier with the DC bias feedback loop.